coming to an end almost, like, this is lab number 6. We have 2 labs to go, and almost there is very little left in our labs. Lab number 6, is about testing of steel beam in bending. So we will take a steel beam and we will try to bend it and see how does it react to the bending moment. So this test will be a little bit different from what we have done in the past in some sense. And I will explain when time comes what are those differences. Okay, now, so here, as usual, I try to connect you to of what we're doing today against what we have done in the past. So in this slide here, I'm showing you the tension test, the compression test, and also the bending test. And I want you to try to see what is the relationship between the force direction and the axis of our element. For example, look at compression. So when you look at compression, you will see that the compression force we applied along the axis of the specimen. And so you can see it is perpendicular to the cross section. So the cross section is this way, and the force is normal or perpendicular to the cross section, and that's why it causes a normal stress. The normal stress that the compression causes, it's simply uniform. And what does it mean uniform? It means the entire cross section will be under the same amount of stress. For example, everything will be 50 MPa. Everything will be 100 MPa. So uniform, everything is the same. Tension, pretty much the same, no change. Only thing what we do is we reverse the direction of the force. Where, but still, the force is acting along the axis of the specimen, perpendicular to the cross section. So the stresses will be, again, will be normal stresses and also uniform. It means the entire cross section will be subjected to the same level of stress. So that's tension and compression. So today, what are we doing? We're really bending a beam. So I'm showing you here on the top left, like a little bit piece of a beam. And please understand there is a support here. So the beam is supported here and also supported at this point. And what we're doing is we're applying our load. Remember, in this case, the load is perpendicular to the axis of the beam, perpendicular, not along the axis of the beam, perpendicular. And you can see my beam will bend down this way. And if we take a little bit of the beam, like this part, and put it here, this is what happens. You can see the beam is bent. So what happens here, the top fibers are trying to shrink, and the bottom fibers will be elongated. Do you guys get that? Like the bottom fibers of the beam will get longer, and the top fibers of the beam will get shorter. Is that something you feel it? When we bend our beam, the bottom fibers will get longer and the top fibers will get shorter.
Yeah.
Okay, how this compared to the tension and compression? I'm asking you, in tension, what happens to the entire cross section? So everything gets longer, and in compression, everything gets shorter. So that's why when you look at the stress diagram, it is not really uniform. Okay, I'm gonna zoom in and to show you what's happening here. So this thing in green is the stress diagram. This diagram was constant on tension and compression, same type of stress. However, when you bend your beam, really the stress value is not uniform. It varies. As you can see, the top fibers will have the maximum compression stress, and the bottom fiber will have the maximum tensile stress. So hopefully you can see this is one big difference between tension compression, and on the other hand is bending. Okay, there are some other differences which I will point out later on. Now let's move on to this picture here. And this picture, to be honest, it's not really like before when I try to show you where in my structure where twist or maybe bending, sorry, compression or tension is happening in my structure. However, I just want to ask you one question here. One question. If I ask you to simply walk under this roof, would you feel safe or unsafe?
Very unsafe.
Very, very unsafe. I agree, and I will do the same thing. This looks like there is excessive deflection. The beam, for some reason, maybe it was overloaded. I don't know what happens, but obviously the beam is deflected so much. And that's why I want to show you when a steel beam deflects too much, this is not really a good sign. And that's why in the next year, like in your second year, when you learn about steel design, that's one of your courses called steel or structural steel design. When we design our beam, it's not only about making sure that the beam is not going to fail. And obviously, I'm asking you, those beams, are they failing? Are they on the floor? No, the beams are still in place. However, they have excessive deformation. And that's why part of our design, and that's something you will see next year, is that to limit the amount of deflection. So we design for strength, that we make sure that our beam will not fail under the load, and also under loads, we get acceptable amount of deformation. And also this picture shows you how the beam bends. Look at this beam. The bottom fibers are in tension and the top fibers are in compression. Now let's look at our test for today. Our test, as usual, we follow one of the testing standards. So our test today designation is ASTM C393. And in this test, really what we're doing is we're applying a bending moment on a beam. Okay. So why are we doing the test? Why are we doing the test? If you remember, we have done the tension test and compression test and also the torsion or twist test for one reason, to find some design value, like for example, the modulus of elasticity or the shear modulus. And those numbers, you will use them in the design process next year in your steel course. So why are we doing this test for this morning? For a few reasons. Number one, you know, there is something called elastic beam theory, and this theory is trying to explain what happens to our beam as when we apply bending. So really, one of the objective of this test is to show you and demonstrate for you how the beam would behave under bending moment. And to do so, we're going to test a steel beam, okay? Not concrete, not wood, steel beam. And you will see here in my slide, there is something called G40.21. So don't worry about those numbers. I'll explain in details later on what those numbers mean. It's a steel beam at the moment, it's just a steel beam. And you will see also on this beam, we will apply load and we also will measure some strain. Okay, so we will fix the strain gauges. If you don't know what strain gauge, please wait. I promise you before the end of the lab, you will understand what those guys do. Next is, we would like to compare between bending stresses calculated using Fletcher formula. So in this class, I'll show you the formula and we can estimate the stress using this formula and also compare it against what do we measure using the strain. Then finally, we would like to see illustrate the development of shear stresses in the web of the beam. I know, to be honest, I know at this point of time, there are so many things are not very clear on this slide. That's why I'm asking you, please be patient. Before the end of the class, you will know more about those objectives. Now let's look at the test setup. So as I said, we're using a steel beam, a steel beam. So steel beams are simply or not typically in most cases, those are standard sections. Steel beam in most cases are standard section. Yes, we can fabricate our own by getting some plates and cut them in one shape and weld them together, but this is not the norm. It happens only when we don't have available standard section for us. For example, bridges. Bridges are super, like the spans are long and the loads are high, and those ones that we get from the mill is not really enough for us. And that's why for bridges, we simply built up our section from blades. However, in general, in most cases in building and other construction, we use standard sections. So I'm going to, to take you through the process a little bit, not really very deep, because you will have a deeper discussion in other classes. So here we're using something called the W section, W section. And the way we call W section is by saying W and then number and then by another number. You can see here I'm using H and G, and I will tell you later on what is H and G. For example, we say W 200 by 100. And let's understand what this means, okay? So first of all, W is something called white flange beam, which looks like an I, like letter I, and I will show you a picture soon. But the word W means white flange section. The 200, this 200 number here is simply the height or the normalized height of the beam, okay? It's the height of the beam, so basically it's this dimension, not the height of the beam. And then 100 is simply the self weight of the beam in kilogram per meter. So if I take 1 meter of the beam, then the self weight will be 100 kilogram. Now, I'm going to show you what W section is. So I'm gonna probably fast forward here, and your W section looks like so. Looks like an I, letter I, and even in some countries they call it I beam. They call it W section and I beam. Okay. Uh, Now, if you want to get more data or more details, I put here there is a website which you will use in your lab if you don't have the book. Okay, so let's go to this website and see the website. It simply tells you all the available sections in Canada. Okay, you can see here. Just all you have to do is just visit the website on the link that I provided on my presentation. It will get you into this page here. Okay, and you can see letters like W, S, M, HP, WWF, and so on. So what are those names? Those are standard sections. The mill will fabricate them, and we as designers and engineer and builders, we use them to build something. Okay. There are something like L. So anybody can guess what's L? How does it look like, the L? L?
L-shaped.
It's exactly L shape, like an angle, like L shape. So this is one of the standard section. Again, I'm not going to go into the details of all of those. There are some hollow sections and pipes, stuff like that. My discussion will focus on W. So when you click on W, you can see it's not only one beam. There are so many sizes of the beam. For example, at the very bottom here, we have a W100, goes all the way on the top to W1100. The beam on the top, it's a monster height. It's a kind of, it's a W, it's a I beam, and the height is about 1100 millimeter. Okay, so that's pretty big. Again, but even with this 1100, it doesn't work for a bridge because bridge span is super big, loads are so high, so it doesn't fulfill our requirement. Now, when you think about the W1, for example, W200, okay, when you click on W200, what happened is you will see some sub beams. What does it mean, sub beams? It means even from W200, we have several versions. We have at the very bottom here, W200 by 15, okay? If you remember what 15 means, it means the weight of the beam, self weight of the beam per meter. So every meter will weight 15 kilograms. How about this one? What does it mean? Any help? Like W200 by 100? Any help? So W200 by 100, it means the beam height is about 200 mil, and the weight, the self weight of the beam is 100 kilogram. So for sure, this one, W200 by 100, is way heavier than W200 by 15. Let's go ahead and click on one of these beams and see what do we get. If I click, for example, on W200 by 19, what do you get? Can you read? You can see here, the website gives you all the properties of this section, starting from the top. So we call it W200 by 19. And there are some other information like something called D, okay, and something called B, and something called T. I know this is kind of mysterious. So what is B, what's D, what's T? If you are curious, all you have to do is go down and you can see here, there is one link called View Symbols Legend. So when you go to View Symbols Legend, what happened is here, it tells you, for example, what is B, which is the width of the flange, what is D, somewhere here, D, and it's alphabetic, huh? So the D is the depth of the section or the height of the vertical leg. And if we go back to our section here, so now we know what is B, what is D. You can see the height, it is not really exactly 200, huh? So the height which is of the beam is not exactly 200. So although we call it W200 by 19, but the height is not exactly 200. It is normalized, which means kind of an 8-inch thing, huh? 8-inch beam. Now, really, one of the things on your exercise is you have to figure out which W200. So in the lab, I'll show you quickly the lab, and then we switch back to our discussion. So in the lab, it simply gives you all the measurement of your beam. So I'm gonna draw a rectangle right now. So here are the measurements of the beam. So which, for example, the flange width is 132, the beam width is 206.05, and so on and so forth. So what happens here, the first exercise in your lab is to identify this W200 beam. It's 200 by what? And it's not super difficult. All you have to do is you do the following. For example, you go here and click on W200 by W200 by 19. And let me ask you, do you think this beam in our test is W200 by 19? Is not secret. Huh? All you have to do is you just have to compare between the depth, and then B and B, and then T and T, and W and W. If those numbers matching, then this will be the beam that we're using. Okay. So let me ask you right now: what do you think? The beam in our test is it W200 by 19 or something else?
Something else.
Thank you so much. Obviously, look at the width of the flange. The width of the flange here is 102, and the width of the flange here is significantly larger. There is almost 1 inch more. So what does it mean? All you have to do is you just jump from W19 to W200 by 22, and then just do the comparison one more time. I'm asking you, is that W200 by 22?
Nope.
Okay, finally, look at this. So I'm going to go to the next one, which is W200 by 21. Can you please check for me? What do you think? Is that the same W or not yet?
Not yet.
Okay, so you know what? I'm gonna let it for you. The next one is your beam, and I will let you guys to do that on your own, huh? So anyway, so now we know what is W section, and we know how do we call those W sections, how do we call them? Now, before we leave this slide here, there are a few things I want everyone to see. So on the beam, we fix something called strain gauge. Look at the name, strain gauge. So those strain gauges are small elements that we can glue and stick to our beam. And what they do is they measure the strain gauge. So they measure the strain. So a few observation here from this slide is that how many strain gauges did we fix or do we fix on our beam? You can see the number, huh? We have total of 9 strain gauges. Seven of them, they are at the mid of the beam. So at the mid of the beam, center of the beam, we simply fix 7 gauges. More important is that the gauges are oriented horizontal. So are oriented horizontal, and they are at varying depth. So the number 1, for example, is on the top flange, and number 7 is on the bottom flange, and number 4 is on the neutral axe. Look at this name, very important, huh? Neutral axe, very important. Okay, and 2 and 3 in between, 5 and 6 is in between. Okay, so those are 1 through 7. How about number 8 and number 9? You can see they are not in the middle, they are just above the support, and you can see the support is here, so they are above the support. And one more thing is they are oriented at 45 degrees. So this angle here is a 45-degree angle, okay? Because this is connected to our discussion later on. Now, also, if you are questioning what is G40.21M 300W, as simple as this is a steel grade. You guys have seen this, huh? In your labs, you have different steel grade manufactured according to different specification. So we have to give them a name, okay? So G40.21M 300W, it means it's one of the steel grades available in the Canadian mills. Now here is the test. So this is a picture of the test. I want you guys to quickly compare between this picture here and this picture here. They are exactly the same. This is the actual test, and this is the schematic for the test. Something I kind of forget to mention, which is how do we load our beam? You can see here the beam has total span of L, and the way we load the beam is we load the beam in 2 points. So one point is here, another point is here. And I will explain for you later on why do we load the beam in 2 points. So you can see we have a distance called A, which is how far the load from the left support. And the distance in the middle called Z, and it's kind of equal, it's kind of symmetric. So we have A from each side, and we have Z in the middle. Now I'm gonna switch, and probably I'll give you 1 minute here, 1 minute there. I want you guys to see the similarity between the actual beam and the schematic, okay? When I say look at the similarity, I'm asking you, do we have, from this angle, I know it's very difficult to see, it's an I beam or W section, but one thing, do you see the support? So do you see the support point? I need some confirmation, please. Do you see the support point?
Yep.
Okay, do you see also the strain gauges? So the strain gauges are connected using wires. So all those wires you can see here, for example, this is strain gauge number 8, and you can see close to the support at 45 degrees angle. And number 9 is not really, it's hiding behind the column. So it's over there, and it's also at angle 45 degrees. Now, how about the 7 strain gauges in the middle? Where are they? Simply, those are the strain gauges in the middle. Where is number 1? Number 1 is here, okay? Which is on the top flange. Top flange. Where is number 7 is hiding below. You cannot see it from this angle. Where is number 4? Number 4 here is in the middle. And then you can see 2 and 3. So this is 2 and 3. And then 4, 5, and 6. You can see, again, 1 is on the extreme fibers in tension. 7 is extreme fibers in compression. 4 is in the middle. 2 and 3 is on different depth. Why I'm keep repeating and repeating and repeating? Because you can see this is connected so much to the discussion coming. Every location of the strain gauge will dictate how much strain in your beam. Okay. Now also look at how the beam is loaded. So the machine will push here. So that's the load coming from the machine. And we have kind of a bridge. So this kind of a bridge. And what this bridge does, you can see it splits your load into half and half. Okay, do you see that? I need confirmation. This bridge here splits the machine load into 2 halves. Like if I apply here P, so P over 2 will go here, and then also P over 2 will go to the other side. I need some confirmation.
Yep.
Okay, last piece, and then we move to the test. This guy here, you can see this, you see this gauge here? There is a gauge here, and the gauge is connected to the underside of your beam. What this guy does is simply, when we apply load, we know that our beam will deflect down, will go down under the load. However, because of the beam is so strong and the span is so short, we cannot measure this or see this by our bare eye. It's very, because it's very little, huh? Probably it's a fraction of millimeter or maybe a millimeter, which is very hard to see. How about the gauge? So the gauge is very accurate, and it will simply measure deflection. Deflection, okay? I want you guys to understand the difference between deflection and strain. So the strain is simply the change of the length of those fibers divided by the original length of the strain gauge, okay? While deflection is simply how much this beam goes down under the load. Okay, now we're ready. Now we can roll and show you the test. So before the test, I want just to confirm this is another schematic because you need this to find the moment and the shear in your lab. So you can see here, I applied here B, which is the load, and we have a bridge that splits my load into two, huh? So half of the B goes here, half of the B goes here. And so we have here two diagrams. You are required in the lab to draw those diagrams, but with numbers, huh? With numbers. So this diagram here is called the shear, which is very simple. The shear force, it's equal to the reaction of the support, which is P over 2. For example, if I apply here 30 kilonewton, okay, it means my reaction here is 15, and my reaction here is also 15, okay? And which means my shear here is equal to 15 kilo newton, okay? Now that's for the shear. Remember, between this point and this point, can anybody tell me what's the shear? Between this point and this point, how much is my shear force?
0.
0. Thank you so much. And that's exactly the secret. Why do we do 2-point load? Because you can see where are my gauges, like from 1 to 7, they are, all of them, they are here. Huh? 1 to 7, they are here. Those are my strain gauges. So I'm asking you those. Are those strain gauges measure or has business with the shear forces? Remember, they are installed in the middle, and in the middle, there is no shear force. It means when I measure strain here, those have no business with shear strains. Okay? You guys following? The reason why we have 2-point load is that when we have 2-point load, then this section of the beam in the middle will be under only bending moment, no shear force at all. Now, the next one is something called M diagram, which is the bending moment diagram. Very simple. Simply, it looks like what you see here, like a trapezoidal shape with a value of PA over 2. So P is your load, which is 30. In this example here, A is how far from the load from the support, and we already give you this distance in the lab is equal to 333 millimeter, okay? The total length of our beam is 1 meter, and it's kind of split it equally. So 333, 333, and then the one in the middle is 334, okay? So how much is this number? So it's 30 kilonewton, that's my load, multiply by A, which is the lever arm, which is 333 divided by 2. The only thing I would like to remind you is the units. Please mind the units in this exercise here. So when we estimate the moment, we want to estimate the moment in kilo newton meter, okay? And you can see this number is in millimeter. So that's why when we do the multiplication, we have to divide this number by 1,000 to turn it into a meter. Okay, we're ready for the test. So that our test here, I have 2 videos, one video for loading, another video for unloading. So let's watch the video, and I want everyone, because simply the strain gauges, you cannot see anything because you can see there are some wires. The wires go to the back where we have kind of a screen where we can record the strain measurement. While really what you can see in this whole test is simply the gauge. So as we add more loads here, we get more deflection, and this gauge will start to move. Please watch. So this is the loading part of our test. Okay, so I'll show you another video where we simply remove the load. So you can see here we started this video from where we have already some measurement in the dial gauge, and then we started. Okay, you can see we already have removed all the loads, and I'm hoping that you guys have seen the movement of the dial, where the dial went back to exactly where it started from. And so you can see here, my beam is so elastic. When I apply load, it goes to one amount of deflection. When I remove the load, then it goes back to no deflection. And as long as we are in the elastic limits, if you guys remember what the elastic limit means under tension and compression. So there is one point, if we pass this point, which is called the yield point, if we pass this point, what happens is here is that we get permanent deformation, so our beam will never go back to its original shape. Now, can anybody notice a big, huge difference between this test and the other tests? It's a huge difference, okay? Anybody noticed the big difference between this test and other tests? Looks, guys, it's still early in the morning. Did you have your coffee?
Is the load spread out over two instead of being in one point?
No, I didn't mean something else actually. Like, look at this. So I'm asking you, did we break our beam?
Nope.
How about tension, compression, impact? What did we do for our specimen? We destroyed the specimen. We destroyed the specimen. And that's why really what I wanted to say is that this test is non-destructive test. Non-destructive test. You can see the beam is intact. And actually, to break this beam, we need a lot of force. So that's why we cannot break it here. And there is no point of breaking it. Okay. Now, let's move into the theoretical part of our class today. We talk about beam theory and so bending theory. And what bending theory said or claiming is that when we apply bending moment, to our beam like so, and so this bending moment will simply cause all the fibers above the neutral axis to be in compression. Okay, look at where I'm hatching. So all those fibers of your beam above neutral axis. Where is my neutral axis here? It's in the middle because of the symmetry. So anything above neutral axis will be in compression, and anything below neutral axis will be in tension. And what happens here, the beam theory said, when we apply bending moment, so I'm going to show you a side view of your beam. So if you draw a straight line on the side view, I'm sorry, my line is not really very straight, but this is how the cross section will look like before the load. What if I apply some load? What happens is beam theory is saying this plane here will rotate linearly. So you can see it will be still a plane, but it will rotate due to bending moments. What is this picture here? Simply, that is the side view of your beam. So what does it mean? It means on neutral axis, it means it has no change. It means no strain here, so zero strain here. And as you go away from neutral axis up, the amount of strain will increase. Where is the maximum strain? Any help? Where is the maximum strain?
At the end of it.
And on the top fibers, on the bottom fibers, you can see here the maximum strain at the extreme fibers of the beam, which is the top. So this point here and this point here, those points, they have the maximum strain. So you guys know that there is a relationship between stress and strain. You remember, huh? There is a relationship between stress and strain. When I increase the stress, when the strain is increased, I increase the strain. When the stress is increased, the strain will increase. And that's why this diagram here, so this one here is the strain diagram. Also, it's the same thing. The same shape applies for stress diagram. So you can see here the sigma, and this sigma is the stress. So you guys remember in my class here, in my lab, did you learn with me that sigma is equal to F divided by A? You remember that? The stress is equal to the force divided by the area. You remember that? Anybody remember that we estimate the stress equal to the force divided by the cross-section area?
Yep.
Yep.
Okay, so this one here, this is how we estimate the stress from axial forces. So how do we estimate the stress from bending moment? So if I apply a bending moment on my cross-section, how can I estimate the stress? You can see here, there's another sigma here, and this sigma here is the stress due to bending moment, not axial force. Very simple. It is simply M divided by something called I, which I will discuss later on, multiplied by Y. M is the applied moment. So whatever moment that you apply, so it's the M, and then I is something called the moment of inertia, and then Y is how far the fiber from the neutral axis. For example, let's say I want to estimate the stress here, okay? I want to find the amount of stress here. Very simple. All you have to do is, this is your Y. This is the Y of the point, okay? And obviously, where do I have the maximum stress? Where do I have the maximum stress?
The farther your Y is?
Exactly. So really the maximum stress is happening here at the top fiber, where Y is maximum and equal to the height over 2. Okay, you know what? I will switch to my next slide because it has more discussion in more details. This is very handy. Please watch this slide. So one more time, how much is my M? Simply, this is my bending moment. What is I? I is something called moment of inertia, or sometimes in some other literature, they call it second moment of area. It's one of the properties of the section. And how can I find the moment of inertia? You don't have to calculate it yourself. Look at this picture here. Can anybody tell me how much is my moment of inertia for this beam, which is W200 by 21? Again, I know it's difficult for you, but let's go to this page here, which said about the symbols. Okay, which one of those symbols represents the moment of inertia? Can anybody tell me? IX. And if I scroll down, you will see IY as well. Somewhere here, you will see IY. Okay, and I know some of you are wondering, why do I have 2 moments of inertia for a beam? Any help? Anyone can guess? Because the beam has 2 axes, so there is one axe. Let's say this is your XX axis here. So if the beam bends around this axis, I need to use IX. And if the beam bends around this axis here, like this is YY axis, so I need to use the moment of inertia in the Y. Again, you don't have to estimate this yourself. You just go to the table, and I'm going to ask you right now, how much is my IX for this beam? For W200 by 21.
19.8.
No, that's not right.
Oh, 19.8 is not right?
No, it's not right.
Okay.
Because watch this, watch this. That's why I insist for some of you to read. The number is here. It's 19.8 times 10 to the power 6 millimeter to the power 4. Okay, so really the moment of inertia is not 19.8, it is 19.8 times 10 to the power 6. And that's why I insisted for some of you to read yourself. Okay, the moment of inertia is 19.8 times 10 to the power 6, and the measurement unit is millimeter to the power 4. Okay, so be careful about that. Also, the y is the distance from the neutral axis, and the y maximum is how much? Simply the y maximum, or the maximum stress, is happening at half of the beam. How can I get half of the beam? Any help? Can anybody tell me in this example here, how much is my y?
That'd be your D.
So that's D. How much is my D? Can anybody read?
203.
Exactly, but the y is equal this number divided by 2. Okay?
So 101.5.
Exactly, sir. Thank you. So what happens here? Your y is equal to half of the beam height. You can see the y is measured from the neutral axis, and the height is twice of that. Really, please mind the units. Mind the units, because I'm asking you, normally, how do we measure the sigma? What are the units for stress? By now, you should remember that, huh? What are the units for stress? Anybody remember from tension test or compression test?
Newton per millimeter squared.
Thank you, sir, which is MPa. So if this is once, we get this one in Newton per millimeter square. I'm asking you, on this side here, what should we be doing? Remember, if I want to get the left side in Newton millimeter square, looks like everything on the right side must be in millimeter. So let's investigate, let's test. What are the units of the I? Millimeter to the power 4. What are the units of the Y? Simply millimeter. So what's the problem? The problem is this guy here. Typically, when you estimate this guy would be in kilo Newton meter. What should I do? What you need to do is here, okay? Simply, you take your moment, you multiply it times 1 million, and this will turn your moment into Newton millimeter. Very important, huh? Otherwise, your numbers won't make any sense for you. Okay, so last thing is that's the last. So the last thing is, you can see we can estimate the sigma based on the moment divided by the moment of inertia multiplied by I. But don't forget, you guys remember this equation? Anybody still remember this equation? We had it in our class in tension and compression. Sigma, the stress, is equal to the E, which is the modulus of elasticity, multiplied by the strain. Anybody still remember this equation? I know it's kind of weird because in my class, this is how you have seen the equation. You said E is equal to sigma divided by epsilon. That's how you found the modulus of elasticity. But remember, there is no difference. It's the same equation. We're just rearranging the term, huh? So the sigma is equal to E multiplied by epsilon. Do you guys remember? Hello.
Yeah.
Kinda.
Again, look at this. E, when you find the slope of the line, you said E is equal to the stress divided by the strain. Okay, and then he went ahead and found the slope of the line. So that was, remember, this was the sigma, and this one was the epsilon. And simply, it's a line equation. Think about it as x and y. Huh? Think about x, y. This one is the slope, so y is equal to mx. The E is the slope, it's your m, and epsilon is your x, and sigma is your y. That's pure math. So sigma is equal to E multiplied by epsilon. Now I'm asking you, did we measure epsilon? And remind me, please, what is epsilon? Anybody remind me what's epsilon in this equation?
Normal strain?
Normal strain. I'm asking you, did we ever measure the strain? Did we measure the strain in this test? Hello?
Yeah. Is it the gauge strain from your 1, 2, 3, 4 points?
Exactly. I know that I have never showed you so far those reading, but I'm telling you, we have those strain gauges and we have the reading. So I'm asking you, did we measure the strain? Yes, we did. Now I'm asking you, can we estimate the stress from the strain measurement? So if I know this number, like the epsilon, and the E is 200 gigapascal, can I find the value of sigma?
Yes.
Exactly. So look at this, please. I know this is a little bit confusing, but watch what I'm going to say. So the sigma in the top, on the top, is simply measure the stress. It's stress that we measure because we measure the strain and we multiply the strain from the strain gauge measurement multiplied by E. I get simply measure the stress. How about the stress on the bottom, like M divided by I multiplied by Y? What do I get here? I get an estimated stress. So really, those numbers, they supposed to somehow match. Now, let's move on to, I think this is our last slide, then I will take you through the lab. So our last slide here is simply, we're done with those. So we're done with those. So right now we focus here on the site, which is another strain gauge oriented at 45 degrees, close to the support. And remember, close to the support, what happens when I go to the support? Number one, the moment will die. If I need to remind you, that was the moment diagram. So if you go to close to support here, okay, how much is my moment? Is almost zero. How about the shear? We have the maximum shear. And what this means, it means my strain gauge number 8 and 9. Look at this, strain gauge 8 and 9. Those are close to the support. What do they do? Strain gauge number 8 and 9, what they do is they measure strain, but not due to bending moment or normal stresses. They measure strain due to shear stresses. Do you guys agree or disagree? I'll say it one more time. Strain gauge from 1 to 7, this section here, it has a bending moment, but has zero shear. Agree or disagree?
Agree.
How about 8 and 9, which they are very close to the support? What's happening to the bending moment? Dies, zero. How about the shear? It's the maximum. So I'm asking you, do 8 and 9 measure strains due to shear stresses?
Yeah.
Yes, so here we go. Here is a discussion, very simple discussion about shear stresses. How do you do? Number one, originally there is like, here is your support. So here is your support, and it simply have a force like B over 2, correct? So that's the support, that's the reaction. And then so this is your shear. And so there is another shear going downward from the load. So here we have a load here, which is B over 2. P over 2, that's the load. So this one here is your reaction, and that's the load. And you can see this is your shear force. And shear force, by definition, if that's the axis of the beam, our shear force are simply perpendicular. So this one is going up, and this one is going down. We're trying to shear the section. You know what? When you look at this small element here, just by having this shear forces, it's unstable. Why it's unstable? Because this element will rotate. Look at this. We have two forces, and there is a lever arm in between. So this simply will try to rotate. But the beam has a homogeneous material. So the beam itself will say, no, no, don't rotate. I'm here. So the beam will develop in its horizontal fibers a shear that simply balances the rotation. So again, look at this. So this force here and this force here is simply the shear forces, while this force here and this force here called conjugate shear. And those are developed by the beam itself to stop this element from rotation. Look at this. So I'm going to show you, this arrow here, it shows you the moment from the conjugate shear, while this arrow here, it gives you the moment due to the shear. You think they are opposite, huh? Do you see that the directions? They are opposite. Okay, and that's why this element here is stable, it doesn't rotate. Now you guys know from statics that if you have two forces, again, forget about this one for now. If I give you one force here, another force here, are you able to find the resulting force? Like let's say F1 and then F2. Did you learn last semester how to find the resulting force? I'm asking you, the resulting force, is it going to be this way? Tell me, is it going to be this is the R? You think that's right or wrong?
Wrong.
Wrong. The resulting force is always in the middle, okay? And F1 and F2, if the two forces are equal, where is my R? If the F1, F2 are equal, where is my R? The resulting force. It simply bisects the angle, huh? If the two forces are equal, then the R will bisect the angle in between. Our angle here is 90 degrees, and that's why the resulting force here is R, and this R will simply bisect the 90, which means at 45 degrees, okay? By the way, you can do the same thing on the other side. You can simply take this force and this force, and you can make the resulting this way. It will be your R, and that's why this element here, we can simply replace all those shear forces by two orthogonal forces, tension and compression, okay? Tension and compression. It depends on the orientation of the strain gauge, okay? I'll say it one more time. You can replace the shear and the conjugate shear by by the resulting force. So it will result in tension and compression in two orthogonal direction. Two orthogonal. I'm showing you in the sketch number 3, this one here, I'm showing you the direction of the T or the tension, and this one direction of the C. So really it depends on the direction of my strain gauge. If I orient my strain gauge this way, I'm asking you, what do we measure? Tension or compression? If I orient my strain gauge this way, what does it measure?
Tension.
Tension. How about if I orient my strain gauge this way? What does it measure?
Compression.
Compression, exactly. So let me ask you here, let's look at strain gauge number 8. Forget about number 9. I'm asking you, strain gauge number 8. What do you anticipate? Does it measure tension or compression? The answer is here, by the way. The answer is here. Okay? Look at the orientation of the strain gauge number 8 and compare it against this one and this one. Okay?
Yeah, compression.
Compression. Okay? The tricky one is number 9. I know that maybe most of you will fail to know 9 will measure tension or compression. Any thoughts?
Tension, maybe.
Yes, thank you. Did you guess, or you know why? You know why? Does it measure?
Just because it's opposite.
Exactly, it's the opposite, it's the other end, so it will measure simply tension. You know what? We have concluded our lab today. Really, the left for me is to take you through the data that we have. Okay, so you can see here we already went through this one. So you can see here is my A. The length is 1,000. The A is 333, so that's no surprise. We already mentioned those. We already discussed the dimension of the beam. How can you use them to find your exact W section? Once you know your W section, you can find the moment of inertia from the table. Remember, those numbers are available in the book. And if you haven't bought the book, then the website I provided can simply do it for you. Now, time to look at the readings that you have never seen so far. Do you think what are those readings? Here we go. So those are the gauge readings, the strain gauge reading. How many of them you can read? We have 1 through 9, so we have 9 gauges. And the thing is, we have 2 groups of observation. So this group of observation is simply for a load of 30 kilonewton. So that's at a 1 load level. And we have another set which corresponds to 60 kilonewton. Now, I want you guys to observe with me something that's happening already, and this will confirm your observation and understanding through this lab. I'm asking you, do you remember where was gauge number 4? Number 4. Where was gauge number 4?
The middle.
In the middle. So what do you anticipate for the strain in the middle?
0.
Remember, that's neutral axis to 0. So I know some of you say, okay, here is the 0, so that's correct. How about this -2? What is it? Why we get -2 here? Maybe it's difficult for you, but that's called the measurement error. Any measurement we do in our life, and I'm saying any, I mean any. So any measurement that we do in our life, it contains certain level of error, sometimes due to the electronic noises, stuff like that. So those are errors. So theoretically, this number it's supposed to be 0, but it is -2 because of the measurement error or the noise. Now I'm asking you, what should be the relationship between reading of strain gauge number 1 and strain gauge number 7? what is the theoretical relationship between the strain gauge of number 1 and number 7 reading? Any help?
They're the furthest from the middle for like on the web.
Remember, 1 is on the top fiber, 7 is on the bottom fiber. Do you agree?
Yeah.
So in terms of reading, what is they should be the same or should be different? What do you think?
It should be the same but opposite.
Should be the same and opposite. So this is, by the way, this was my next discussion. You can see here there is a negative number. It means any time you see negative number, it means this is a compression. Anytime you see positive number, you can see this means tension. But in theory, this number here, the 102 and the 98, they supposed to match. Why we're getting like kind of a four units error? This is measurement error. Okay, I need someone to help me, please. Can anybody tell me what is the reading on gauge number 2? I need some help. What is the strain gauge reading at strain gauge number 2 with load 30? Anybody can help me to read that from the table?
So the second one from the top.
Can you please read for me?
65, I mean like compression.
Okay, you know what? I know sometimes I'm super pushy. I push you to read for me for a good reason, because really it's not really 65, not minus 65, because look at this. 65 is multiplied times 10 to the
10.
power minus 6. So, okay, so that's why all those readings, the units are to the power minus 6 millimeter per millimeter. And you can see this is unitless, which is our strain is unitless. So please make sure when you do the calculation, every one of these numbers are multiplied by 10 to the power minus 6. Now, finally, I want to ask you, if I know that the stress here is 98, sorry, that's the strain. Can anybody find for me what is the stress corresponds to this fiber? So I measure the strain. It's minus 98 times 10 to the power minus 6. Can I get how much the stress at this point? Did I teach you anything a minute ago or a few minutes ago on how to find the stress if we know the strain?
Multiply it by the elastic modulus.
Thank you, sir. Perfect. I really appreciate that. So all these numbers, if you multiply them by the modulus of elasticity, simply this will give you the stress corresponds to at these fibers. Now let's look at the lab itself. So here is the lab. Okay, I'm trying to be clear and show you everything to minimize your question in the future. So here is your lab. First thing you want to do is copy all these numbers, or maybe replace this page here by this page here. And you don't have to copy them. So those are the measurements that you're supposed to have taken them in the lab, but we give it to you. Next is, you can see question number 1 is asking you to draw the bending moment and shear diagram. And I know this is, you will ask this, so please watch this. So this question is only about how to draw the bending moment and the shear, where in my presentation I will give you a reference. So this page will allow you to draw the bending moment diagram and the shear. All you have to do is replace the P with 30 and then one more diagram for P equal to 60, okay? So in the question number 1, you need to draw the shear and the bending moment diagram corresponds to the two load. You can see here, draw the shear force and the bending moment diagrams corresponds to the 30 and the 60. Okay, the question number 2 is, it simply tells you enter the strain gauge data in the chart below and draw the best fit line. Okay, for example, look, watch this. So all you have to do is you're trying to draw the gauge from 1 to 7. Okay, so please don't include 8 and 9. So it's only from 1 to 7. And what you have to do, let's do it. So we have here a minus 98. So on this picture here, you simply draw a point at 98. Let's say here. So that's your 98. We have a point here. And then on gauge number 7, I go here, I read 65. Okay, so you come here and then you draw 65. So 65 is somewhere here, okay? So this is gauge number 2. Gauge number 3 is 35. So we draw another point here, 35. So 1, 2, 3, 35. And then finally, your 0 is roughly about 0. It's, let's say, 2. I'm asking you, what do you anticipate if I connect these points together? Does it give me a parabola or line or what?
Should be a line.
Line. And that's exactly what the beam theory said. The beam theory, it says that when you apply bending moment, your section will rotate, your planes will rotate in a linear fashion. And so really what you have to do is, if you have a perfect measurement, what do we get? If we have a perfect measurement, we simply get a perfect line. So all my data point or my measurement will come on a straight line. But the reality is we can never get that because of our measurement error. So what's the best we can do? If you have some data which they contain some errors, what do? We have to do a best fit. So a line that goes in between my data point, and that's called the best fit. Okay? And then finally, guys, really what I want you to do is to show you how to fill this table. Anything else, I'm pretty sure it's really very straightforward. So I want you guys, all of you, to look at this table right now. So this table, you need to fill this table to finish your lab. Okay, so I know table, it will be kind of mysterious. What are we trying to do here? Watch me, please. So we're trying here to fill this part first, okay? And look at the header. It says stress from flexure formula. So what is my flexure formula? Simply the stress is equal to M. I'm going to write it here. So this side here, it comes from M divided by I multiplied by Y. M divided by I multiplied by Y. I'm asking you, I'll ask you one by one. Do we know the I? Do we know the I of our beam?
Yeah, we get it from the website or whatever, right?
Thank you, sir. That's correct. I'm asking you, do we know the Y at top at gauge 7 and gauge number 1? Do we know the Y? Remember, 1 and 7, those are extreme fibers. Do we know the Y at these points?
Yeah, we do from the data, right?
Yes, so that's D over 2. So from the table, you find your D divided by 2. So this will give you the Y. So look at this. So we know the Y and the I. And remember, those are constant. Those don't change. So the I is constant for the section and the Y is constant for the top and the bottom. It's the same number. I mean, for all these calculations, we have 1, 2, and 3, and 4. The I and Y, they are the same. So what's really different between the 30 and 60? Simply, it's the moment. So when we apply more load, like let's say 30, we get one moment. When we apply 60, we get different moment. How much is my moment? Can anybody tell me how much is my moment? M equal, is it connected to the span and to the load? Did I teach you somewhere in my slide how to find the bending moment? P multiplied by A over, sorry, not capital A, just little a, divided by 2. Anybody remember that we can estimate the moment using this equation?
Yeah.
Okay, so I'm asking you, what is the P? What is the P?
30.
Exactly. So here, for these numbers, and for those two numbers, the B is the same, which equal to 30. Okay. For those two numbers here, how much is my P?
60.
Okay, now I'm asking you, how much is my A? What is A? Also, I mean, I'm not asking you to memorize, but just if you can remember that. So in my slide here, if I go here, what is my A?
333.
Exactly. It's how far my point load from the support. So at 333, as I said, be careful about the units, because this moment here, it has to come in kilonewton meter. So you have to divide your 333 by 1000. Now, so we have done this part already. How about this part? I'm pretty sure that some of you will say it, we want to find the stress, but not really from the formula, from the Fletcher formula, but from the strain gauge measurement. Can anybody tell me how can we estimate those four numbers? Hello?
Are we getting our E from the graph we graphed before and then multiply by a
No,
strain?
the E here, I'm asking you to use, I'm asking you to use E equal to 200,000 MBA, 200,000 MBA. Okay, so I'm asking you, if we know that the E is equal to 200,000, how can I find the stress from the strain gauge measurement? We've done it already. That's not new, huh? So I think all you have to do is you look at this table, you take the numbers at 1 and 7. So we have four numbers, huh? One is minus 98. The other one is 102. The third one is minus 198. The fourth number is 201. And what do we do with these numbers?
Multiply them? Are you saying the 200 is what we're using, or we're
Multiply by 200,000, and this will give you those four numbers. My question for you is, how this number should agree? Like, for example, you know what? I know that there are so many texts here, so I'll clean a little bit, huh? If you don't mind, I will clean a little bit. Okay, now we have filled our table. I'm asking you, what should be the correspondence? Watch this. I'm asking you, how this number should match this number? How well should match? It should well match very, very well, because you can see this is our top fibers at the stress at top fibers, and we have two values. One value here is simply measured from or calculated from the Fletcher equation. Another one calculated from the strain gauge measurement. Now we can see by the same token, this number and this number, they should match to some extent. This number to this number, they should match. This number to this number, they also should match to some extent. Why they don't 100% match? Any reason why they don't 100% match? 100%, I mean exactly. We said it already, guys. We said already why those numbers they don't 100% match.
measurement error or what?
Yes, sir. Thank you so much. Because of the measurement error. Those strain gauges are like a little element, which probably includes some electronics, and any electronics will have some sort of noise, huh? So anyway, we're done for our test. The last question is about to draw an element, which is simply this guy here. That's really what number 5 is all about, this last slide here. So all you have to do is copy either T or either T, and we are done for today. So really, at this point of time, I will simply ask you, do you have any question before we break?
Yeah, that website, where is the link for it?
It's below in two of my slides. So if you go here, the website is here. Also, it's another page, which is here. So the link is available on 2 slides.
Okay. And then when you were saying use E equals 200,000, is that the value we're supposed to use, or we're going to calculate, like we're going to get it from the graph?
No, you cannot find the value of E. You just please use a value of 200, which is typically for mild steel. This will be the value for the modulus of elasticity, 200,000.
200,000, and it's unitless, like
200,000 is megapascal, huh? Or 200 gigapascal. That's modulus of elasticity.
Oh, okay, right. Alrighty.
The strain is unitless, huh? The epsilon is unitless. The strain is unitless. But the modulus of elasticity has the same units of the stress, which is a megapascal or a gigapascal.
Okay.
The 200,000 is megapascal. The 200 is gigapascal.
Gotcha.
Any other questions? Okay, guys, now it's 9:10, and we will have 10 minutes of break. You guys know what to do. We'll leave this channel, and when you come back, you go to your breakout groups. And then I will leave it, for example, to the last maybe 10 minutes. I'll come back and ask you if there is any question. You can see I'm going into so much little details to minimize those questions.